For many centuries, scientists have been trying to solve differential equations. Often it is difficult to solve these problems by hand, or it might even be impossible. Therefore, we will now take a closer look at a very simple method to approximate partial differential equations, PDEs, which is still used in the industry. Let me give a quick tour of finite differences. Overview: finite differences. The finite difference method consists of the following steps. Step 1. Write down the PDE. What is our problem description? Step 2. Decompose the domain. We make our problem finite dimensional. Step 3. Approximate derivatives. Insert finite difference approximations for derivatives into the PDE. Step 4. Assemble linear system with finite difference tensor. We write the PDE that has been approximated with finite differences and discretized on a grid as a linear equation system. Step 5. Solve the linear system. Step 6. Visualize and post-process solution. We have to answer the following questions. Firstly, is our solution plausible? Secondly, how good is our approximate solution? Quantitative error estimation. And finally, how quickly does our approximation converge to the analytic solution? Computational convergence. Model problem: Poisson's equation. Let us now analyze our model problem, Poisson's equation. It reads minus Laplace u equals f in the domain omega and u equals 0 on the boundary of the domain. Now we have to specify how the Laplace operator is defined. It all depends on the dimension d of the domain of the function u. In general, the Laplacian of u is just the sum of the second spatial derivatives of u. Or more concretely, in 1D, the Laplacian is the second derivative. In 2D, the Laplacian is the sum of the second derivatives with respect to x and the second derivative with respect to y. In 3D, the Laplacian contains also the second derivative with respect to z. In the following, we will restrict our analysis to the two-dimensional case and can thus insert the definition of the Laplace operator into the Poisson problem. Decompose domain. Until now, we haven't specified on which domain we are solving the Poisson problem. In this video, we will work with the L shape, which is a square from -1 to 1, from which the part inside the first quadrant, its upper right corner, has been removed. To reduce Poisson's equation to a finite dimensional problem, we now need to only solve the PDE in a finite set of points from the L shape. This can be done by dividing the domain with a grid. Here the mesh size h equals 1/4 is the distance between two parallel grid lines that are directly next to each other. At each point where two grid lines intersect, a point ui is placed, and the equation minus Laplace u equals f needs to be fulfilled there. Furthermore, at the points on the boundary, the red circles, the solution should be 0. Assemble linear system. The core idea of the finite difference method is to approximate derivatives in the PDE by difference quotients. The formal definition of the derivative is f prime of x is the limit of f of x plus h minus f of x over h as h goes to 0. Please note that for small values of h, this quotient is a good approximation of the derivative. However, in the Poisson problem, we only have second derivatives. For the second derivative, we get by Taylor expansion that f double prime of x is approximately f of x plus h minus 2f of x plus f of x minus h all over h squared, which holds true for small values of h. This formula is called the central difference quotient. Now let us go back to Poisson's equation. If the equation should be fulfilled on the entire domain, it should also be fulfilled in our grid points u1 up to u33. Here we use the notation ui for the value of u at the ith point and fi for the value of f at the ith point. We can then approximate the second derivatives of u with respect to x and y by the central difference quotients and insert these formulas into the PDE. This can be simplified to 1 over h squared times minus u of xi plus h, yi, minus u of xi minus h, yi, plus 4 times u of xi, yi, minus u of xi, yi plus h, minus u of xi, yi minus h, which equals fi. This difference quotient is known as the 5-point stencil and can be represented by this matrix. Going back to the decomposed domain, we now go over all grid points and show the equations that we get from applying the stencil. When applying the stencil, we also account for the fact that the function u equals 0 at the boundary. After looping over all grid points, we can now regroup the equations, which can also be written down in matrix notation. Overall, we get a linear equation system with 33 unknowns, which can now be solved if the right-hand side function f is given. Now let us solve the linear equation system. For that purpose, let us choose the function f to be equal to -1. Physically, this means that the uniform force, like for example gravity, acts downward on the L shape. We are computing the displacement u, which is 0 at the boundary. When it comes to solving the equations, remember that our matrix is quite small, and thus we can solve the linear system with a direct solver like the LU decomposition. However, if we were dealing with much larger linear equation systems, for example with more than 1 million unknowns, we would need to use iterative solvers like GMRes instead. This is the end of our quick tour on finite differences. Thank you for your attention.